All right, today we're going to talk about real basics on filters. So if you might be new to the hobby or old to the hobby, but just not really well versed on filtering and all the technical details of stuff, we're going to try to break it down to keep it real basic and really get a fundamental on what filters are doing in FlightOne and in Betaflight. Okay, so there's a lot of similarities between FlightOne and Betaflight for filtering nowadays. They both primarily focus on low-pass filters. There's one differential is Betaflight has a notch filters and a static notches and a dynamic notch, where FlightOne is mostly low-pass filters, but they do have a predictive filter as well, which is not I don't know if that's exactly a low-pass filter, but I believe the other ones here are basically boil down to different variants of low-pass filters, first order, second order, and we're not going to get into all those details. We'll talk about what a low-pass filter is in just a second, but just looking at the two screens here, you usually have two stages. You have a stage 1 filter and a stage 2 on the gyro, so this is the gyro filtering, and on Betaflight you have the same thing here as well. You have a low-pass 1 and a low-pass 2. As far as I'm aware, it doesn't really matter if you have Stage 1 is the higher number and Stage 2 is the lower number, or vice versa. It looks like that's a little bit reversed, like in FlightOne, usually Stage 1 filter is usually the higher, but in Betaflight, usually Stage 1 filter is usually lower. Either way, they're just running through the math in a cascade, so it doesn't matter if it does one then the other, so on and so forth. So you can see, again, FlightOne, Stage 1 and Stage 2 on the gyro, and then also you have a Stage 1 and Stage 2 on the D term. And then same thing for Betaflight. You have a Stage 1 and Stage 2 on the gyro, and Stage 1 and Stage 2 on the D term. Now Betaflight, you have these additional notch filters you can turn on, the static notches, which I don't really recommend using unless you have a specific piece, but we're not going to get into all the details on that. So what is a low-pass filter, and what are these filters doing? I think the best way to demonstrate that is just going into Betaflight, going into the Sensors tab, and then you can click on Gyroscope. And just grab your quad and hold it at arm's length, as steady as you can. And you can see that although I'm holding it and looking at it and trying to be as steady as I can, there's just micro vibrations because I'm just not that steady. And the gyroscope's picking that up and making that, that's a X, Y, and Z is the roll, pitch, and yaw axis, and you can see all those oscillations or vibrations that, in reality my quad's being steady to some extent, right? But our gyroscopes are honestly, they're just kind of too sensitive. Well, that same thing happens in the air. Now I just put it back on the desk. That same thing happens in the air, just at a higher frequency. So those peak-to-peaks, those vibrations, those are called frequencies. And when your motors are spinning and the props are humming, at 30, 40,000 RPMs, there's a lot of vibrations there, and our gyros pick all that up. They pick all that motion up. So we can look at that in a black box log. So if you run a black box log in FlightOne or in Betaflight, you can record the raw noise, and that's what this is. The debug 0 here is roll, and then we're looking at the filtered roll axis after the low pass filters and the notch filter, and Betaflight's example. And you can see the raw noise is all these little vibrations that it's picking up, honestly, from the motors and the props vibrating. That's what it's hearing. And if we would not filter that at all, it would drive the PID loop crazy, specifically the D term, because the D term reacts on the magnitude of the slope, and you can see how steep this slope is, so the D term would really spike up. The D term is like a noise amplifier. It just, any vibrations coming in, it just really amplifies it, and so we need to filter that down to get, because in reality in this is just a full throttle punch. We're not moving roll or yaw. The quads, it's not even windy. It's not being blown around by the wind. This is just the vibrations of the motor. So our gyros are just really too sensitive, and we need to kind of break that down. So through some low-pass filters and whatnot, you can see the signals, and you can still see there's vibrations in there. Ideally, that filtering, it could be more. You could filter it even harder than I have it filtered here. But unfortunately, there's a side effect of filtering. So whenever you're filtering anything with any type of filter, there is this thing called phase delay. And if you can look right here, you can see the gyro signal coming in. This is during a roll move, zero throttle, just doing a fast roll. And the filtered gyro signal is offset from the actual raw. And there's really no noise here either. It's kind of straight. Well, what is that? That's the phase delay, and that matters. That makes a difference in prop wash and flight performance, and it's pretty far. I mean, if you look here, what you can do to measure phase delays, you can see this is 211. You hit the M for mark point, and you start moving over until the other one gets to 211, and you can see how far that phase delay is. And that phase delay is around, it's a little bit above less than 1 millisecond. It's 2 milliseconds is 500 hertz, so we're kind of in between there and getting around 211 here, and you can see the differential between these two pieces. So again, that phase delay during prop wash, and really it's a prop wash issue. During prop wash, that offset, essentially the data going from the gyro to the PID loop, to make it blunt, is wrong. It's always wrong because filtering makes the data wrong. It filters it out, it smooths it, but then it offsets it in time, and that offset in time means it's lagged and latent, and then the PID loop's reacting to old data. The quad is kind of moved on, it's doing something else before the PID loop's reaction even gets back out to it, so it just gets behind. Now, it's not super latent, so it still flies really well. 1 millisecond is not really that bad, but if we can make it 0, that would be ideal. But none of the filtering I've seen to date has 0 latency. So these filtering, like low-pass filters, notch filters, what is this? It's really old math. It's used in the audio industry, and they'd say, our quad, it's not sound. It's exactly sound. I mean, sound is just vibration of the air. We are filtering vibration on the frame. Both are vibration. Sound is no different than the vibration. So we're using essentially tried and true audio methods of filtering. So when you turn down the treble on your car radio, that is a low pass filter. You're sliding that low pass filter down, and this is what one looks like. So this is the amplitude. You'll see graphs like this around, and a lot of this I just wanted to kind of get a base fundamental, because you're going to have to see these graphs and get used to them. This is the amplitude that it's attenuating. So wherever this line is, like right here, when the sound is less than 600 hertz in this example, let's just say 500 hertz right here. When the sound is less than 500 hertz in frequency, that means it's not attenuating the amplitude of that sound coming in. So back to black box here, this is the full amplitude of the sound, right? The red line from top to bottom. When it's attenuating half of that, that means it's reducing that overall signal in half. That's what this graph means if the attenuation was right here. So sound that's at 600 hertz in frequency, it is attenuating 0.71. So it's about a quarter of it, 25%. It's a little more. It's almost 29%. It's taking whatever's coming in the amplitude of that vibration and cutting it by a quarter. If it'd be 0.5 by half, so on and so forth. So you can see this cutoff is defined. So that cutoff is just, it's kind of really arbitrary. It comes from the audio industry. That's wherever a low-pass filter cuts by 0.71 in amplitude, or negative 3 decibels. They'll use decibels a lot. It's the same thing, just different ways to say it. So that's what a low-pass filter is. And then you can set this cutoff, so you can say, oh, if I move this cutoff way back here, any vibration above, say, 100 hertz would be attenuated pretty steeply, you can see here. And this talks about a stop band and transition band, all these kind of things. And in reality, there is no stop band. So this is kind of an ideal, and you can play a little audio file. I'll drop a link here. You can play a little audio file of different voices at different low-pass filter settings. So that's what a low-pass filter is. It's just you set a cutoff, and then above a certain, basically above the cutoff, and honestly below it as well, noise is attenuated and reduced in amplitude from that frequency higher. So a notch filter, what's a notch filter? This is not exactly a notch, this is a band stop, but they're kind of close to the same. A notch would come down to 1 point here instead of, and not have this gap, this band stop in between. But essentially you have a low pass and a high pass filter working in conjunction, and it will cut out very specific noise. Now what's the advantage? Why wouldn't you just cut it all out? And the reason is, as notch filters have, at the center of the notch, they have infinite attenuation, and they have very little phase delay associated with that. So they're very, just how the math works, it's very good at attenuating right at the center of the notch. And it can really cut out peaks of noise. And our motor noise is peaks of noise. So let's jump over and just kind of look at this. So you can say, well, frequency, what are you talking about frequency? Well, if you just measure these vibrations, if I go from the peak of one here and hit my marked point, and then I go to the peak of another one, that noise, that vibration is at 419 hertz. So you can see that's kind of in relation back to that low pass filter. If it's below the 600 hertz in this example, so it's not being attenuated really well, if that's where our cutoff would be. If I had a notch filter, by example, and I had that centered right at 419 hertz, it would smooth this out completely. So if I had a notch filter centered right at 419, this would be completely smooth through here, because that's kind of where notch filters accelerate, just hitting certain peaks and bands of noise. So how can we look at these frequencies, how spaced out the vibrations are for the entire flight? Well, in Black Box Explorer, you can just click the button here, and this does a fast Fourier transform, is what they call it, and it essentially just analyzes that for, what are the vibrations, amplitude, and frequency. So it just kind of graphs them, essentially. It's just a graphing exercise. Okay, so after a little bit, it graphed them on. I can hit the little expand button here, and you can see across the entire flight, this is our frequency. So there's more noise, higher in amplitude. So see, this is the amplitude from top to the bottom. Higher in amplitude right here, and there's a lot of it, that is at 452 hertz. So that's the spacing. Same thing down here. Well, if you really, once you get into this a lot, this area from here to here is where my motors are. Generally between 200 hertz, you can see this is 230, so generally between 200 hertz and 600 hertz on like a 5-inch quad, that's where your motor band is. That's just naturally with the props spinning at 30,000, 40,000 RPMs and the motors and the frames we're using, that's where those vibrations are, the spacing of it, and then the amplitude varies. Like if you have really noisy props, this amplitude might be gigantic. If you have very good props, it might be pretty low or stiff frame. Now when you get into micro quads and whoops, that moves up. So a 3-inch micro quad, that motor band might start at, 400 hertz. 300, 400 hertz, it kind of starts, it has a larger range, and then it goes all the way up to like 800 or 1,000 hertz. So your motor band is really a lot longer, and it just has a more variety of frequencies in there for where those vibrations are happening. Now the amplitude is less, right, because it's lighter props, lighter machines, so on and so forth, but the extent of the frequency range, the variation of where these peaks are, is a lot longer. So what are we trying to filter out, and why are we using low-pass filters? You can see in here, this low-pass filter is set at 100 hertz. We got some D-term low-pass filters as well. Anything really above, let's say 70 to 80 hertz, is just vibration noise, and we don't want it at all. And anything below that is really just raw motion. You can see these huge spikes here. Those are the raw motion of the quad, moving left, moving right, low frequency, because it's just, when you stick right, that humps up in the gyro signal, but it's the frequency of that, the space between that is really, really low, 1, 2 hertz. But the amplitude, how much it varies, is super high. So if we back up here and we look at this, the motion here is really extensive, but the frequency from this peak to the next peak, where I would maybe bank right again, is really far apart, like 0.1 hertz, something like that. So that's why it shows up like that in the spectrum analysis, all really far down here. So we really want to filter out everything up here, leave everything below, say 70, 80 hertz. Prop washes starts around 30 hertz, and if you get your PID set really well, that frequency moves up, and you can get up to like 60, 70, maybe 80 hertz. Around there. So here's a little bit of the variability, and I'll drop this link below. This is a little spreadsheet I have that shows you kind of the differential. When you look at this ideal graph of what a low-pass filter is, this is just, kind of university talk of what a low-pass filter is. In reality, and this would be a first-order low-pass filters, there's different ones. First order means there's no exponents in the equation. Second order means there's exponents, 2, third, exponents of 3, fourth, exponents of 4. The higher the exponent, the more phase delay, but the more attenuation it can give. So just jump back to here. So I have a little Excel file I developed earlier in the year. If you haven't used it already, I'll drop the link below to it, and you can download it and take a look at it. And it's specifically set up for Betaflight. I do want to do one for FlightOne. I haven't gotten there yet. But you can see the difference between the ideal or the math class, the university class of what a low-pass filter looks like, and in reality, what a first-order low-pass filter looks like. So this is a first-order, and in Betaflight it's called a PT1 low-pass filter. I'm talking about this filter right here. See, PT1, and we'll talk about biquad in a second. In FlightOne, that is the frequency filter. They call it the frequency filter. Both are first-order low-pass filters. Hopping back to here, you can see I have it. Well, you can't see it yet, but I'll show you in a second. There is a cutoff set of 600 hertz, just like in that example here. But you can see it's not nearly as steep, doesn't go down to 0, only goes to half. So even at 1,000 hertz, you're only reducing the amplitude by half. It's not as effective as this would make you seem to believe here. Now in this sheet, what we can do is we can change this cutoff. So say we can put it at 100, what is more what we normally see. Now you can see at 100 hertz, things change. And now this is what the low-pass filter is. You can see wherever that cutoff is, it's always going to be attenuating by 0.71 the amplitude, right? So at 100 hertz, now at 1,000 hertz, you're going down to 0.1 of the noise amplitude, and so on and so forth. You can see the profile. And you can even see prior to the cutoff point, you're attenuating noise all the way back to 25 hertz. So from 25 hertz up, you're starting to attenuate the noise coming in. So that's a first order low pass filter. With this sheet, you can turn on multiple in series. So I could go ahead and turn on 2 of those and see what those look like. So now we have 2 at 100 hertz. Let's just make this one at 200 hertz. So you have the one, the other one, and then this is the total of the 2 in attenuation. You can kind of see the results you're going to get there. Now here's the downside of those. They have phase delay. This is the phase delay that you're going to get from those. This is the motion area. This is the prop wash area. Like we said, goes up to about 80 hertz. So we don't care about phase delay above 80 hertz, right? Delay it all you want. We're not using that data to fly the craft. We're using this data and this data. So we do care about this phase delay here, and it's shifting that signal off by 3.5 milliseconds. So here's the trick with filtering. How can we attenuate the most with having the least amount of phase delay? And it's a trade-off. There's no free lunch, unfortunately. So for this, let's talk about what's a second order low pass filter look like. So we're going to change this to biquad. So in Betaflight, a biquad is a second order low pass filter. And in FlightOne, a biquad filter is a second order low pass filter. So what I did here is I have the PT1 as the orange line, that's a first order low pass filter, and a biquad, which is a second order low pass filter, as the blue line. Ignore the gray line for now. I have them both at the same cutoff frequency. So you can see the difference in between the shapes. A biquad filter doesn't attenuate lower bands, but it does attenuate higher and steeper after the cutoff filter. So it's less attenuation below the cutoff and more attenuation above the cutoff. And say, oh, that's great. Why don't we always just use biquad filters? Well, you can look down here in the chart. You can see that biquad filter has much more phase delay than the low pass. But let's see what happens as we move things up. So we go up to 150 hertz for the cutoff on both. You can see how they look in attenuation, and now that phase delay is starting to get closer to each other. And you can see if they're both set to a cutoff of 200 hertz, the phase delay differential between them's not that bad. It's not that the differential in phase delay between the two gets a lot more palatable. And you can see that the biquad is attenuating a lot more. What's also nice about the biquad is it's not attenuating your lower frequency noise below the cutoff as much as well. So you can, you're not attenuating the actual raw motion as much. So now let's turn on a notch filter. So now we have a notch filter at 200 hertz. So if we specifically had noise at 200 hertz, we could set a notch filter on top of that, and you can see the amount of latency with that. That's not too bad. It's lower than both low pass filters, and the attenuation strength. You can see this burnt orange line is now. You can see there's a heck of a lot of attenuation. It really goes down to absolute 0 at the absolute center of the notch. It's very narrow though that it's at absolute 0. So those are the differentials. So the next really big question is, why do we have gyro filtering And then we have kind of the same thing for the D-term filtering as well, like same options, right? And same thing here in Betaflight. Why do we have gyro filtering, and then why do we have D-term? What about P-term? What about I-term? Well, in reality, the only reason we're doing filtering is because of the D-term. Just of how it works, the D-term is reacting to the slope of the gyro signal. So when this gyro signal, this filtered one, is sliding down, the D-term's pushing up to oppose that. And you can see that simply by overlaying the D-term then on top of your gyro signal. As you can see, every time this slope, the filtered gyro signal is going down, D-term's going up. When it goes up, it goes down, so on and so forth. So I like to say that the D-term just really fights against any gyro movement. It doesn't want it to move one way or another. The steeper the slope of that signal, the higher the D-term pushes against it. And you can see it's kind of delayed here, and that's because of the D-term delay. So back to it, it was discovered a long time ago, instead of just filtering so heavily the gyro signal, if we split off some of that and just filter the output of the D-term before it went out to the motors, that we wouldn't have to filter the gyro signal. You got to keep in mind, filtering on the gyro signal, that means the P-term reaction is delayed, I-term, which really doesn't matter, and then the D-term as well. So instead of delaying all three, why don't we just delay the problem child here, the D-term? So applying filtering to him, and it kind of helps split the load up a little bit. And I guess the final thing that people wonder is, okay, this is great. How do I set these things? Well, that's for another video, another topic. I was hopeful with this video to put out enough fundamental information that you can watch those other videos as they come along and come out, because it's, we're constantly evolving in that there's new Betaflight 4.0, for example, is going to have new dynamic low pass and dynamic notch features as well. FlightOne has a predictive filter, which is a variant. Yeah, I'm not exactly sure how the in or outs of that work. The fundamental filters, though, are the frequency filter, the biquad filter, as we talked about. This is a first order, second order. This RCEF2, that's just another first order low pass filter. That was something earlier in this year. Same thing with the fake Kalman filter. That's just a first order low pass filter as well. I think these have both of these should have 2-point smoothing on the end, which really doesn't make a difference unless for 8,000 to 10,000 hertz and above. It just, on the lower frequencies, it just doesn't make a difference. This brick wall filter, from what I understand, for FlightOne is a fourth order low pass filter. So imagine that biquad slope even steeper, but then there's a ton of phase delay. So I think the brick wall is a great filter if the cutoffs are super high, because you could see as those cutoffs got higher on the biquad filter, the phase delay became less. And once you get up to 5, 6, 700 hertz, which you would need for 32K sampling, which is what FlightOne does, that brick wall might be a great higher cutoff filter to really just squash out any high frequency noise. Not too sure on the OG filter, but hopefully somebody can comment on that down below in the comments, and then I'll pin that. The other thing you can do in FlightOne is they have filter presets here, ready to use filters. So you have default, low, medium, and high. You can check those out by clicking use on each one and seeing what the settings are here. Honestly, to set filters other than just trial and error and guessing is you really need to have logging where you can see your raw noise, and then be somewhat educated on where to set the low pass filters. Okay, so that's it. Hopefully that was enough information, but not too much information. Filtering is somewhat complicated, but hopefully it's really basic, enough where it's just, there's some low pass filters and where are those cutoffs going to be, and hopefully we cover enough fundamentals that you can watch other more advanced videos if you want to and understand what's going on and understanding some of the tools you're going to see in front of you. I know from my video perspective, you're going to see the Excel spreadsheet all the time, you're going to see plasma tree graphs all the time, you're going to see spectrum, black box spectrums. So hopefully with this, you'll understand when you're seeing those things and then have some sort of introduction to filtering and how you can set it up in FlightOne or in Betaflight. All right, everybody. Thanks again, and I hope this did help.
Ideas.